Thank you, Dave, and screw you, Jarrett. Alright, I've got Jarrett here telling me to talk more during my stream. Dude, if I knew I had viewers, I'd be talking the whole time. Don't text me, put it in the chat. Make it seem like people are interested. Music is from the game Exapunks. It's a really good programming puzzle game from the wonderful folks at Zachtronics. I bought the album because it was cheap and it was good. It's really good. It's perfect for programming. Do you want to know? You want to know what I'm doing, Jarrett? I'm making a mini compiler for a little scripting language. Got a couple hundred lines. Remember that Bitwise guy I was telling you about? I'm mainly I'm kind of following the pattern he set forth, and I want to follow his work into the compiler that he wrote. But for now, I'm just diverging and trying to do my own thing and see what I can make with it. Currently, I'm working on tokenizing. So the whole process is, this is some test code. This is kind of what the language looks like, right? It's just a string composed of, you got things that could be names of identifiers, you've got numbers, you've got plus signs, more names, and white space. The process of tokenization, yeah, both. I'm making like a little scripting, like so far, I have implemented math. That's it. No variables, no if checking, no loops. Variables are coming next. But like this works. So if I, well, it would work, except I'm changing the code right now. Okay. I can demonstrate it in just a second. Let's see. Val. It's right here. What the heck? You want to initialize it? Fine. Alright. Alright. So now I'm going to debug. I'm going to step through the code a bit. Compile. It's a stream. And this starts the parsing process. You can actually kind of follow what's going on just by reading the code the way it's written. So the first thing we're going to do is oh, I haven't finished that either. Let's not parse the assignment statement. Let's just parse an expression. Yeah, so we see that the first token is an integer. So we're going to push the appropriate instructions into the code buffer. By the way, I'm not compiling to any actual code. I can show you after the compilation's done. It's just I'm compiling to my own bytecode that this function then executes. Which is basically how scripting languages work. Python, Ruby. If you ever see a Py object file, that's compiled Python. That's compiled into its own custom bytecode format, and then the Python, the actual Python executable, Python.exe, just loads that bytecode and executes it. So it's one level removed from the machine, but it lets you do more convenient things. And it's also nice because you don't have to learn x64 assembly. I'd like to eventually work to that point, but that's down the road. Get actual real code running on the machine. Alright, let me start that over. Let's skip the actual parsing code. Let's just compile it. Let's see what we come up with. Okay. Alright, so right now the code is just a buffer of numbers. But these numbers correspond to this enum here. Under the hood, C will convert this to 0, 1, 2, 3, 4, 5, and 6 respectively. Oh, actually... Yeah, you know what? Let me interpret this as a pointer to opcodes. What are lit and get actual version of Windows? No. It hasn't been a problem except one time my taskbar was stuck and yeah, I can't personalize my PC until I activate Windows. I don't have that kind of money. I just graduated college. Alright, so the idea for the virtual machine is a stack machine. What's the best way to demonstrate? Probably a spreadsheet. Okay, the idea is I'm gonna have the code over here. Code, not the stack over here. What's my code? It's 5050. Actually, let me just read it and I'll compile it in my head. Wait, that doesn't make sense. Let me look at what's actually in the memory. Okay. 5, 5050503. That doesn't make sense. I broke something. Did I break the integer code? Oh, I think I did. Right, we don't advance it until we're sure we're inside the branch. Okay, so our code should make more sense now. It's not going to respect macros in there. Okay. This is going to be a little whack. And then we should be able to take the len of that. Frick. It doesn't let you use... That's so dumb. Okay. That's what I want. Yeah, I'm trying to explain something that should have taken 2 minutes, but the setup for finding what I needed took longer than I expected. Hold on, we're almost there. 5, 1. Da 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 da. Where's the opcode table? Hey, look at that. right? Alright, we can actually, let's see. Define named range. Opcodes. Done. We can make equals v lookup. Search key there. Ranges opcode. Index is 2. True. Well, that's a lie. Okay, you guys still with me? I'm ready to explain now. Throw an oh yeah in the chat. Alright. The code for this expression right? Simple math, right? We do parentheses first, so 2, 8 divided by 2 is 4, 1 plus 2 times 5 plus 4 becomes 1 plus 10 plus 4 becomes 15, right? That's what we should end up with. So this code it generated should produce a 15. This is how a stack machine works. The only memory access you have access to is the stack. You can only push or pop things to the next value in the stack. You can't do an arbitrary lookup. The lit opcode, what this code does, it reads the code and executes the opcode depending on what it is. So if we get an add opcode, we'll do something, sub, etc. What the lit opcode does is it just pushes the next value onto the stack. So the next value is a 1. We'll put a 1 onto the stack. Then a 2. Then we'll put a 5 on the stack. Multiply. It just multiplies the last 2 values on the stack, 5 and 2, and puts the result at the top of the stack. So we have 10. Add. Same thing. Adds the top 2 values of the stack. We got 11 now. Now we add more literals. 8. Then lit 1. Then lit 1 again. We execute this add. This becomes a 2. We execute a division. This becomes a 4. There should be another add here. Well, there must be, because the code worked when I ran it. So the last add would turn this into a 15. Let me halt, and that's the result. Because these are binary operators, so for instance, this plus, it's only adding the result of yeah, that's chiller. This add here, which corresponds to one of these add instructions, I don't remember which, it adds the result of this computation and this computation. So it's only ever, and the multiply only works on these two. All these operations are binary. The trick is getting it in the right order so that the instructions execute respecting the right precedence, so that the multiply happens before the add, for instance. So that's why we do all the work parsing the code to work out the structure. You know, at the top level, there's one expression that's composed of an add expression, which is composed of this add expression, which is composed of this multiply. The other half of the original add expression is a divide expression that contains an add expression. So I do all the parsing work. As it goes through parsing, it generates the code that relates to the structure and then runs it, and it works. Result is 15. So, what I'm working on today, I'm trying to beef up the lexer to support more integer types. So for instance, you can type that, it's just a regular number. You can type, you can type a hexadecimal. You start with 0x and then, you know, the classic or a binary. We start with 0b, the rest will be interpreted as a binary number. Right now all it supports is this. And I mean, the algorithm for running through, you know, if you're given a block of text, like I run into these numbers as a string, and I want to convert it to an actual value. You know, just like in Python, if you type, you know, int of some string, all it does, it goes through, you start your value at 0, and then every time you multiply it by 10, because you're advancing the power of 10, right? And then you add the next one. So first we'll have a 1, and then we'll turn that into a 10 plus a 2, so we have a 12. We multiply that by 10, we have 120, add the 3, multiply that by 10, add 1, multiply that by 10, etc. And the same thing's going to apply for binary and hexadecimal, except we're going to multiply by 2 and by 16 respectively. So this case works. Hexadecimal. Actually, let's do binary first. That'll be way simpler. Alright, here it's okay to advance the stream. Alright, there's only two cases, right? So if the character pointed to by the current location of the stream is a 0, we just multiply our value by 2. I can't type, else if it's a 1, we multiply by 2, we add 1. That should do it. And if we run into something else, it'll be an error. So fatal. Let's see. Let's test that. Let's do something simple. Alright. One second. Okay, sorry about the break. Alright, we're just gonna compile this regular code, make sure that still works. Our result is a 3. Alright. Let's make these binary literals, right? 0b10. Throw in spaces for readability. This is still 1 and 2. Just written in binary. That broke. Oh. So first we got a 1, right? Let's just walk in this. Stream is 0. Wait, hold up. Okay. We don't need half this crap. What's our stream at currently, and what is our current token? Oh. Okay, scan int. Our stream's at 0b1. Go to the B. Now we're at the 1. Oh, I did it again. Stream. Next token. Scan it. Here we go. Then we could seem to be. It's a 1. Value's 1. Oh, we made another mistake. After we determine what digit it is, wow, I'm dumb. Okay. While stream equals 0, or stream equals 1. Alright. What the heck? Did that put us in a loop? Okay, while stream is 0 or 1. It's a 1. Oh, shoot. Here we go. Let's just run it. Oh my gosh. Just run. It worked. Alright. Let's try it for larger. Let's actually take this whole expression. I'm gonna convert it to binary. Plus 2 times 5, which is 101, plus 8 divided by 0b1 plus 0b1. There should be 15, right? Hey, baby, it works. Alright, we now support binary integer literals. Let's do hexadecimal. Alright, now, I know this code's super messy right now. I have an idea of how to clean it up, but I want to implement the hexadecimal first, then see what behavior is common to all these cases and extract that. So instead of trying to make an if-else case for 16 possible values, I want to make a table. Let me see. Yeah. I don't know what to call this. We'll just call it table right now. Six ints, and we're going to say right 1 2 3 4 5 6 7 8. Do you mean like where do you differentiate between names and numbers if hexadecimal literals can have letters and names can have numbers? Well, the important thing is that a name, at least in my language, a name always has to start with either a letter, lowercase letter, uppercase letter, or an underscore. So, you know, if you want to see it as a regular expression. Or is that how you do it? I don't remember how regular expressions work. And a hexadecimal number will always start with 0x, and then, you know, whatever. So when we go to fetch the next token, the first thing we're going to check, we're going to skip all the white space. And then we're going to see, okay, is the current character a digit? If it is, we know that as long as it's not malformed, and if it is malformed, we'll throw an error, that it's going to be some kind of int. It'll start with 0x, 0b. If stream, where does this correspond to? Yeah, we're assuming that if it starts with a 0, we're going to assume that regular integers don't start with zeros, so we're not going to allow 0, 0, 0, you know, something like that, because it's meaningless. The extra zeros don't matter. We just want to see the 0 to see if we have 0x or 0b. So if something starts with a 0, it can't be a name. Whereas if it starts with any of these, it is a name. And then we can check, okay, if it's alphanumeric, if it's a letter or a number, or if it's an underscore, we'll accept it. And if we get something else, we'll assume that the name just ended. So, I'll write the table. One more of those, and then A equals... I think this is the right way to specify it. But obviously it's not. Do you do it like this? I don't remember. Oh. Oh, that can't be right. See. That's not helpful. I just saw it. I know it's possible. Oh, I guess it's not possible. Okay. One, two, three, four, five, 6. Oh, whoops. And it's B, C, D, E, F. I can do that all with my left hand. You know, it's the little things. Okay. Go away. Go away. What's the problem? Oh. Did that answer your question, by the way? That explanation I gave a few minutes ago? Okay, so now each digit in hexadecimal corresponds to one of 16 values, right? Just like each digit in decimal corresponds to one of 9, or, well, 10 values, right? 0 up to 9. That's why we have the extra digits A, B, C, D, F, because we don't want to make up extra symbols to add to the keyboard. Just support a number system. So I want to support capitals as well. So instead of having a 16, well, it would be 2, 3, 4, 5, 6, a 22 branch if statement, you know. Is a current character 0, a 1, a 2, 3, a 4, or a 5? I just made a table. And we can look at this table in memory. I don't know. I'm just going to run here. Alright, we can go to table. Alright, they're mostly zeros, but look, we have some entries here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Down here we have 10 to 15. We also have 10 to 15 here. Why are they spread out? Why is it so big? How does it work? I'll show you. Oh, I actually have one up already. This is my favorite image. This is my favorite ASCII table image for some reason. I don't know why it's so ugly. Here are the ASCII codes. Our code is made up of ASCII codes, right? So we get to the 0x. In memory, it's actually the byte for 8. And then, where's the x? You know, the byte, 120, and then our digits. So up here, I made a table of the character 0 that'll map to the value 0. The character 0 is actually a byte 48. Hey, look at this. The 48th entry is a 0. 49th is a 1. 50 is a 2. Right? Those are corresponding to the actual ASCII values. And then the same thing for lowercase a up to lowercase f. Right? It's 97 to 102. Uppercase is 65 to 70. And we can verify that. 65 to 70. 97 to 102. So it's just doing a lookup in this table using the actual. We come across a capital A ASCII code. We just look it up in the table. It's a 97. We get a 10, or 65, right? 65, we get a 10. We're golden. So now that we have the this next bit I'm programming will be dealing with the hex numbers, and then we'll be done with that, and we won't have to use it again. Honestly, I probably won't use it again when I'm programming regularly, unless I mature the language to a point where I'd actually want to have that capability for some bit manipulation. But even if I don't in this language, if I can implement it, I can use that in some other language down the road. So what are we going to do? Alright. We're going to advance the stream so it's beyond the X, and now it's pointing to the first digit. While alright, let me think. The stream has to be in a number of ranges. Oh, this will be the fastest way to figure it out, actually. Either the stream equals 0, so our first digit's 0, or if it's not a 0, if we look it up in the table, we should get something that's not a 0, right? The only valid entry that is a 0 is 0. The other entries that map to 0 will be an error, you know. I mean, what's 24? The cancel character. Nobody uses any of these. Not since the 70s, man. Get this crap out of here. So that just checks to make sure we have the valid character. We're going to up the value by 16. And then we're just going to look it up. And we're going to advance the stream. If that worked, I think it did. Then we won't have to look at hexadecimal anymore. We can move on to something else. How will it know if it's ASCII or a string? Well, in C, all strings are just arrays of ASCII characters, right? Like if I what's a good place? Let me try to make an example. If I just printf ASDF. I skipped past it. That was stupid. Our music's done. Let's restart. Alright, let me actually step inside the... Yikes! Let me step inside the code. Alright, this is what I want. Is it? I don't know if that's actually what I want. Oh. Which column am I looking at? Oh, that's not the string I want. Yeah, this is what I want. Okay. So in C, a string is just an array of bytes in memory that happen to be interpreted as ASCII values. Like, I mean, everything in the computer, it's all bytes, right? It's just that we're happening to interpret. I already lost my place. We're happening to interpret these bytes in a certain way. So when I write something like quotes ASDF unquote, the C compiler will take that. It'll actually allocate a portion of memory to store the string, and what the printf function actually gets is the address where that string is. So the printf function is actually not getting, it's not really receiving a whole string. It's receiving the address, which is hex 0080 ADEC, where the string is. And here are the string characters. ASCII A, SDF. No, I don't have the table memorized. This is a little ASCII conversion to help. And all C strings are terminated with a 0. They call it null termination. It's how C code knows you've reached the end of the string. Languages like Python, I think they use higher level data structures to store the strings. Some sort of expandable array that or maybe a linked list of segments. But at the end of the day, all those components of that data structure will just be composed of ASCII bytes in memory. The program is a string of ASCII, right? And I'm writing this code to read this ASCII 1 byte at a time and try to figure out what it actually means based on what I say it should mean. Does that help at all? Look, see, here's another string. Somewhere in memory. I'm not sure what it's for, but it ends with a null terminating byte. And these other bytes here are probably just initialized to 0 because we're in debug mode. Yeah. Yeah, I'm actually, so this is what's interesting, right? The reason there's so many strings packed in this part of memory is because the executable that the compiler delivers, any sort of strings that are in text are just packed together. The compiler copies those and makes a part of the executable just contain pointers to these strings. And then if you generate strings at runtime, you have to actually make either an array of characters. That's how you make an array in C. Or you make a pointer, let's see, string equals malloc, you know, malloc, it's memory alloc. It actually asks the operating system, hey, give me 50 bytes of free memory somewhere. And it says, okay. And then we're going to use that to fill our string with. What makes C different than higher level languages is that you worry about things like these. You have to think on the level of what's actually going on in memory. How is my data laid out at the byte level? And it's a pain oftentimes to have to think about that. You know, that's why higher level languages exist, so you don't have to manage your own memory because it's easy to make mistakes there. But there's no other way to understand exactly how your program's laid out. In some contexts, like high performance, that matters. Games, that's why most games are written in C++, or they used to be written in C. C++ is just C with a bunch of extra stuff, because they want to be able to control exactly what instructions are generated by the compiler, so they can analyze their performance and cut every little bit of fat they can, and also how their data is laid out in memory, because on modern processors, that actually has a huge impact on performance. Because of caches, it actually matters that you pattern your memory accesses in a way that's friendly to the hardware. And higher level languages can do that stuff for you, and it doesn't let you have that control when you need it. I gave you a lot more than you asked for with that question, but that's the stuff that makes C interesting to me. I like the kind of low level, being able to be in control of what's going down, what's going on, and being able to at least imagine that you understand what's happening in the processor. But for most problems, you don't need to worry about that, which is why people write languages like I'm writing now. And obviously one's 1,000 times better than what I'm writing now. So, let's just do something simple. 15 plus 15, right? I'm trying to remember. Oh wait, no. Yeah, that's 15 plus 15. Alright, we already broke. Excellent. Wait, let's look at the call stack. Init stream, next token, we're in compile. Alright. Let's walk through it. Yes, it really was. My first taste of that stuff though was actually, there's a book called, well, there was a course, let's see, Nan to Tetris. Yeah, this is the book, The Elements of Computing Systems. These guys, this is like the early 2000s, they wanted to make a project that explained how computers work from a fundamental level, like down to the hardware, so you actually understand why they work. Not just like metaphors, like, oh, there's little trains of bits and bytes that get carried around. And I have the book, and if I had a webcam, I'd show you. But it goes through, and it starts from the bottom, it goes up. Most people you learn, you know, this is a computer, clicky clicky. Oh look, there's this stuff called code. Instead, they went the other way around. They started, here, let's start with a NAND gate, which is a simple circuit that, you know, assuming like 0 is a low voltage and 1 is a high voltage, which is how it actually works. And look, here's a NAND gate implemented with actual transistors. Right? It's here. If we put in 2 zeros, we get a 1. If we put in 2 ones, we get a 0. If we put in 2 ones, we get a 0. Anything else, we get a 1. Let's assume electrical engineers figured out how to build that. Just this. And just combining thousands of these, millions of these in clever ways, you can build a computer. And they show you how it's done. Like, this is how it starts, right? Oh, if you feed both inputs to the NAND together, so if A is a 0, that means we get 0 and 0, and that'll be a 1. And if A is a 1, we get 2 1s inputted, that becomes a 0. That's an inverter, right? You get the opposite thing out that you put in. A low voltage will produce a high voltage, etc. Like, alright. And if you take your NAND and put an inverter in front of it, you get an AND gate. And if you do this setup, you get an OR gate, right? And you can start composing these functions, these simple circuits, to get more and more functionality, all the way up to a computer. And I worked through that book in high school, and I did the first few chapters. I did the exercises myself, and it was very rewarding. The part where they actually like, here, put these pieces together and make an actual processor. I didn't quite get that done. But then I went to college and had to learn that stuff anyway. The architecture class I took in college was actually scary because all that beautiful simplicity I learned from the book, they take that and be like, oh, that's great, but if you want to make things fast, you have to add this dizzying complexity. Like it's scary just how much is going on under the hood in these processors. I don't want to get into it. But the people that design those things are absolute wizards. Now, let's find out. What? Hold on, man. Okay, init stream. Next token. Let me just make sure I even set this up correctly. 0x, okay. Scan it. Stream is 0. Alright, now we have, let's get our watch window. We have an X. Okay. Go past the X. What? Why is that happening? Okay. Okay, stream is an EAX. You put the character in EAX. Is it trying to test it as though it's an integer? No, it's a char. Okay. Alright. Like, am I crazy? Should be 102, right? And table of 102 should be 15. That should be legal. Oh shoot. Here's something that gets you in C. I'm not sure. Yeah, okay. This is an equality check. This is an assignment. This is saying, here, let's set the current value pointed to by stream to be 0. I mean, that's a bug, but I'm not sure why that would have caused the error. But let's see what happens when we come without it. Okay. Oh, we didn't break. You know what? I think this is bugged though. No, it's not. Yes, it is. No, no, it's not. All right. Locals, val, 15. Okay, we should be good now. Yeah, let's actually look at our code. It's probably lit add lit halt. This will be 6 instructions. Yep. Literal 15, add, then halt. That's correct. And just confirm, yep. Let's do larger. Let's do 255 plus 255, that is 510. Alrighty, we got it. Actually, I haven't, this should just put a literal on the stack and execute. Okay, yeah, that works. So let's do, let's do 64. That was dumb. That should be 64K, right? Yeah. 65,535. Alright. Modulo any major bugs? I'm satisfied with that. Like, you know, though, I'm pretty sure we can condense this code. Let me try a new version. Okay. Okay, we're gonna assume a base 10. If we're gonna do this crap. Base equals 2. Base equals 16. Ha, nope. 16 and then 2. Nope. And then we do our loop. Actually, it'll be more like this, right? I'm sorry. This one. I'm really dumb. This is what we need to change. There we go. Value times equals base. Value plus equals table stream plus plus. What I'm doing here, I'm taking the parts that are the same in this code, right? The while loop, multiply. In this case, we've decided our base is 16. So we multiply by 16, and we add the digit value. And here, we're doing the same thing. We split it up, but it really is the same thing. We're multiplying by our base, and then we're adding our digit value. Here we're not adding anything, which is equivalent to adding 0. Here we're adding, this increment operator is just plus 1, right? And the other cases that's showing up, that's doing the same thing. C lets you put that, yeah, here I'm just saying advance the stream by 1 character. When you see it in the middle of the expression, if it's before, it's saying advance the stream before you calculate any of this. You put it after, you're saying run this entire expression, and then after the semicolon, advance the stream. Just little hackery things to lower the lines of code you write. If you get carried away with that, it's kind of unreadable, but I can read this, and that's all that matters right now. So we're extracting that behavior into this one while loop. We pre-decide what the base is. By default, it's 10. But if we hexadecimal, it's 16. If it's binary, it's 2. So we're going to make this main scan int and test it. Please work the first time. That didn't work though. Just put a breakpoint there. Zero base is 10. Stream equals 0. Okay. Val times equals base, which is 16. And we're adding 15. Well, the heck, that worked. Wait. That worked, so what went screwy? Why is the token int value so high? Let's run this again. Oh! I didn't return. Okay. I want to demonstrate what happened here. What I think happened here. Alright. So scan int, we calculated the value to be the correct answer, right? But that correct answer didn't come in here. It's because we forgot to return. But something still got here. And what was it? go to the actual disassembly that's generated, token int value. Okay. We call scan int. Not sure what this instruction does. But the next thing we do is we move the value that's an EAX into this memory location. And then we move the value that's an EDX to this memory location that's several bytes higher. CAD75CH. The way the C application binary interface works, to my knowledge, I'm pretty sure this has worked in 32-bit systems. I'm not sure if 34. The return value always got put in the EAX register, right? Your processor has multiple registers, which are basically memory locations that are inside the processor for fast access. Next, x64, they're all like names like EAX, EBX, ECX, EDX. That was freaking loud. Those are your general purpose registers. ESI, ESP, this is the stack pointer register. I don't remember what that one's for. But anyway, most of the math that happens in the processor, it uses registers as temporary storage locations. And then it moves those out to memory where they need to go. So the contract that each function needs to make is that if it returns a value, which we declare it does, and this is going to receive the value from that function, it's expecting that the function will put the value in the EAX register, and this guy will receive it. Without returning, is there actually a way I can see what's in the registers? I think there's a window for that. Phew. I don't need any of this crap. Anyway, if we go to the disassembly of this function, yeah. At the end, there should be an instruction to move the last value we calculated into the EAX register. That's not happening. But if I say return val, yep, look at that. We're adding our points here, whatever our thing is pointing to, which is the val variable, into EAX. So that when we return, and we grab our value from EAX and I guess EDX respectively, it's there. That's a little bit of a deep dive into how assembler programming works, which is essentially all what this code gets compiled into. Which is another thing, actually. The reason why I'm doing these giant cases instead of, like, you know, an if check. Oh, if it's greater than A but less than Z, or if it's greater than capital A or less than capital Z. That'd be cleaner to look at, but it actually, this code will just generate a giant jump table. It'll calculate the offset of and jump to, which ends up being more efficient. Now, I'm really not an expert in how this works. I've never implemented it myself. Kind of the goal, if I keep going to through compiler, that I will eventually. So I can say here and say people have told me these are faster, and I understand basically why it is, but it could be that I'm wrong in certain particular cases, and someone that knows better about this stuff will correct me. But that's the beauty of this stream. No one knows better than me, because I only have 2 viewers. Let's mix it up. Let's do 255 plus 54. Right? That's another 255 plus direct integer 5. We should get We should get 515 out of this. Don't care. You know what? No, actually I do care. Our first value is 255. Let's continue. The next value is 256. Oh, right. That's actually correct. And then 5. So if I wanted this to be 255, I actually need to make these all 234, 1, 2, 3, 4. Yeah. What the heck? Let's just do that. 765? Can I do math in my head? Turns out I can't. It's fast as frick, boy. Why are you bringing up Keemstar around here, man? Is no one safe? Alright, I like this code better. Don't you? Look at this. Look at this mess. Who's gonna read this and be like, yeah, I know exactly what's going on? Nobody. You read this and oh look, we do exactly 2 things. We determine the base, and then we calculate the value. That's easy to read. This... Let's get right into the news. No, I actually have a pretty good Keemstar impression. You ready? Ah! Welcome to Drama Alert. Okay, what's the next thing? The next thing I wanted to do variable assignment and usage. And then actually it'd be kind of nice to be able to, well, once I get to that point, it'll be nice to write my code in separate files. But now I'm going to move the language beyond the point where it just handles a single expression, and I want it to handle statements. So all right. What's up? I'm sorry? You got pizza? Oh, I'll come down and get some in a minute. In a sec. I'm streaming, man. I love this song. Bum-ba-dum. Expressions and statements. At the top level, this language is going to be made up of statements. I'll probably get to the point where... Well, yeah. A function definition is kind of a statement, right? Anyway, right now we just have expressions, right? We can do, 1 plus 4 minus 7. That's a 5, by the way, not a 7. This is fine, but we can only calculate one value. In fact, our language doesn't handle expressions right now. It handles a single expression. We want to expand that because we want the program to be made up of statements. A statement might be something like an assignment or a declaration. And right now, we're going to do both. Our single statement we're going to allow is a variable declaration plus assignment. Something like var x equals 5. Or we can do the C way without the colon. I kind of like the colon. We're going to put a colon in there. And if we can calculate, we can have multiple statements, we can start doing things that have side effects in the language and that carry value beyond just, like, this is just a value, right? It doesn't do anything. This is the value 0. We have to execute it to find that out, but semantically, this is a static concept. Once we introduce variables, it'll be more dynamic. We're going to have an assignment statement. Okay, and we're going to have a print statement. My gosh, that is bright. I did it again. So we can actually do more interesting things now. We can say, oh, I don't know, var circumference equals 5 and var radius what is it? Oh, we can say var pi equals 3.14159. And we can say var, no, this is what we want to do. Radius and var circumference equals, it's 2 pi r, right? 2 times pi times radius, and then print circumference. Now, this is a real programming language. We have a collection of statements that are executed one after the other. We have variable declaration, which is just some name, and we're going to give it an expression for a value. It doesn't have to be just a number, it can be any kind of expression. And which will include expressions that include... My gosh, I don't want to actually save this. Which will include references to other variables, because now variables have values. So yeah, it actually might be a good idea to separate the assignment and the declaration so that we can have all our assignments at the top, or our declarations at the top. No, we can check the set compile time. We can just say, you know, if I use some, for instance, if I try to reference circumference before we encountered it, we can just say, hey, we don't know what that is. And in fact, that's how C works. I was explaining the other day to you, Dave, my champion viewer, that C works that way. It just runs from the top down. And for instance, if parse expression 4 wants to get all recursive and call parse expression, it doesn't know what this is until it actually encounters parse expression, which is below it. So you have to put this little thing here to tell the compiler, hey, I promise I'm going to give you a function with this signature. Don't complain at me. Modern languages, you would be able, for instance, to reference something that's ahead of time. Now, what you can't do is this. Pi depends on circumference, and circumference depends on pi. Yeah, that's circular. We're gonna make it simple. We're gonna have declarations and assignments. Declaration is saying, hey, there's gonna be variable A, variable B, variable C. Assignments are gonna be like, okay, name, assignment operator, expression. And I'm probably going to have the semantics so that variables are going to default to 0. So that, you know, if you want to reference D before D exists, or before D's been assigned to, it'll just be 0. It won't be an error. Because the compiler already knows D's here, because it's encountered the declaration. So that's not the issue. It just hasn't been assigned to yet, so it'll just default to 0. So A will be 4, then B will be 8, and C will be -1. That's the next step. After variable declaration and expressions that use variables and our print statement, really the only thing that's preventing this from being an actual programming language is control flow, right? If, then else, while loops, for loops, things like that. I'll probably just have a basic if statement and a while loop. And then we'll actually have a basic functioning language. But that's going to be later. I'm going to go get some pizza. Hope you guys had fun. I know I did. I did not expect to spend that long to come up with, where is it, this much code. But sometimes it just be like that. Take care, my beautiful lads and lasses.